Welcome to Math TV with Professor V. In this video, we're going to learn a little bit more about the comparison and limit comparison tests. Now, this is a continuation video to the introductory video lecture on the comparison tests. If you haven't watched it already, or if you're not familiar with these tests, I'll link it here. Make sure you get just the background, the basic foundation under control, because this is going to be a little bit more of an in-depth and nuanced discussion. All right, are you ready? We're just going to do a quick recap though about the tests. First, the comparison test. So say you have two series and both of them need to have positive terms. That's important. First way you can use the comparison test. If AN is less than or equal to BN, so all of the terms of the first series, AN, are less than or equal to the terms of the second sum of Bn. And we know that the sum of Bn converges, then the sum of An also converges. So basically, if you know that you have some convergent series and you can show the terms of your series are smaller than the terms of that series, you know yours must also converge. Be careful though, because if AN is less than or equal to BN, right? If the terms of our series are less than or equal to the terms of another series, and that sum diverges instead of converges, then you have absolutely no info. The test, the comparison test, is inconclusive. So basically that means you need to pick a different test, because the sum of AN, it could either converge or diverge. And if this idea is a little confusing for you, then hop back over to that intro lecture that I mentioned earlier, because you'll need to check that out. And then second way you can use the comparison test is if AN is greater than BN for all n, and the sum of BN diverges, then that means the sum of AN also diverges. So here's how it works. You have some series, you know it diverges, and you can show the terms of your series are larger, then your series also diverges. Again, you have to be very careful, because if you can show that the terms of your series are greater than or equal to, honestly, is fine, right? Bn, and the sum of Bn converges, well, no info again. The test is inconclusive. So the sum of AN could converge or diverge. So sometimes students don't like using just, direct comparison tests, because it's very particular. You have to show the inequality in just a certain direction in order for the test to yield any meaningful results. Another test that we have is the limit comparison test. So you have two series and they have to have positive terms, and you look at the limit as n approaches infinity of the ratio of AN over BN. And if that limit exists as a positive number, okay, so that limit, we're going to call it C. C has to be positive. So it can't be 0. That's a big deal. And it also can't be infinity. If that's the case, if C is just some number, you don't care what number, just not 0 or infinity, then both series behave the same. They either both converge or both diverge. So I'll repeat that phrase a lot. Both series behave the same. And a lot of times students like using this test better because you don't have to involve any inequalities, right? You just have to make sure that you choose the correct series to compare it to, so that this limit doesn't come out to be 0 or infinity. As a side note, if C is 0 or infinity, all that means is the test is inconclusive. Okay, you have no info, and most likely you chose the wrong series to compare it to. Okay, we'll talk about that more in a minute. So let's get into some examples and distinguish when to use, each test. Sometimes it doesn't matter. You could probably use either. Other circumstances, that's not the case. So let's just build up our repertoire here. All right, directions. Just determine whether the series converges or diverges. We have the sum n equals 2 to infinity of 1 over rad n minus 1. So when we're talking about an, usually that refers to the terms of your original series that you're given, okay? And let's see, what is this sum reminding me of? What are the terms reminiscent of? A lot of the time when you're doing the comparison or limit comparison tests, you're going to compare them to P series or geometric series. Most of the time it's P series. So I'm already getting vibes of P series. I'll consider the sum n equals 2 to infinity of 1 over rad n. I'm starting at 2 also because that's where this index of summation began. Well, what do I know about this sum? Well, it's P series. P is equal to 1/2, right? Square root of n, P is 1/2, which is less than 1. And so what do I know about this sum? It diverges. Okay, so if I'm going to use direct comparison, I need to show that the terms in my series, an, are greater than or equal to the terms of the series I'm comparing it to. That's Bn right there, 1 over rad n. Can we do that? Can we? Because think about it conceptually. If this series diverges, and I can show that each of these terms is bigger than each of these terms, then of course this sum will diverge also. Of course it's going to blow up. So can I show this inequality? It has to be bigger. Less than doesn't matter. Well, let's see. 1 over rad n minus 1. If I compare that to 1 over rad n, I know for sure the denominator here is going to be smaller than just rad n, isn't it? And since the denominator is smaller, I know this overall expression is going to be larger than 1 over rad n. Think about how fractions work. Which one's bigger, 1/2 or 1/3? The one with the smaller denominator, 1/2. Okay. Now that we got that out of the way, did we show the desired inequality? Yep, we sure did. So then we're done. We are totally done. That means the sum, n equals 2 to infinity of 1 over rad n minus 1 also diverges by, and then always cite your sources. Say what test you used. The comparison test. Okay, so if I were to be grading this, if you were in my class, here's what I would need. You say what test, you say what it does, you rewrite the series in question. Yes, you do. You have to show the inequality. Okay, and then you do need to explain or justify how you know what we compared it to either diverges or converges, okay? You need to have that justification. All right, pretty straightforward so far, right? Now I want to change up this problem just a smidge and then have a discussion on how we would have to proceed. So what if instead, and I'm going to change it ever so barely, the sum n equals 2 to infinity 1 over rad n plus 1. So what did I do differently? All I did was replace this subtraction with addition. And now I'm asking you, what would you do? So again, these terms here we'll refer to as an. And I'm still going to compare it to the same P series. Because, you know, adding or subtracting a constant isn't really going to alter the growth or control it so much as that rad n does. So this is still my Bn here. All right. Can I show that AN is greater than or equal to BN? No, I cannot. In fact, AN is actually less than BN. Do you notice? 1 over rad n plus 1. Now the denominator is larger, making it smaller than 1 over rad n. Uh-oh. Does that mean that the series is going to do something different than we suspect? No, this is still going to diverge. It does. It still diverges. How do I know that? Because adding or subtracting a constant, like I said, isn't going to change so much about the growth. It's just now, because I can't show that AN is greater than BN, excuse me, I have to use a different test. I just can't use direct comparison anymore. Well, what's my other option? Well, let's use limit comparison test instead. So when you can't show the necessary inequality, then a good choice is, let's bust out that limit comparison test. So now what I'm going to do is consider the limit as n approaches infinity, 1 over rad n plus 1, that's AN, over BN, 1 over rad n. All right? Good. And then if I'm dividing by 1 over rad n, that's the same as multiplying by rad n. So we have limit n approaches infinity, rad n over rad n plus 1. I want to divide by the highest power of n in the denominator, same as multiplying by 1 over rad n. So we can take this limit. So we have limit n approaches infinity. In the numerator, I'm going to have a 1. And in the denominator, we'll have 1 plus 1 over rad n. All right, so as n approaches infinity, 1 over rad n, that's going to go to 0. And all I'm left with now in this limit is just 1 over 1, which is 1. So what does this tell me? Well, this limit exists as a finite number, right? It's finite and it's not 0. So what does that tell me? Both series behave the same. So when you do limit comparison test, whatever you compared it to, if you get a finite non-zero result from that limit, then your series will do the same thing as the one you compared it to. So we compared it to a divergent p series. That means ours will also diverge. 1 over rad n plus 1 also diverges by limit comparison test. Yes? Good. Both series behave the same as my own little phrase, but I think it'll help you remember. Okay. Let's look at some more examples. Example 2. We have sum n equals 1 to infinity, 5 plus 6 cosine of n over n squared. Okay, so let's think here. Let's kind of take a guess as to what we suspect is going to happen. So this is AN right here. Who's running the show? 5 in the numerator? Nah, that's not doing so much. 6 times cosine n. I mean, cosine n, it's an interesting, cute little function. It oscillates, but it doesn't get too wild. It just only goes up to 1, down to -1, right? I'm more interested in this n squared in the denominator. So this is kind of giving me p series vibes again, yes? N equals 1 to infinity, 1 over n squared. That's a p series. P equals 2, which is greater than 1. So I know this series converges. Okay, if I'm going to use direct comparison, I need to show that AN is less than or equal to BN, right? Where BN are the terms of some convergent series. So let's see, can I bound an? Yeah, I mean, cosine of n is very easy to bound, right? I know the largest cosine is ever going to be is 1. So I could say for sure this is less than or equal to 5 plus 6 over n squared, which is the same as 11 over n squared. Okay, so why don't we go ahead, call this Bn, and I'm just going to slap an 11 here, and we'll talk about why we're allowed to do this. If you multiply some convergent series by a constant, it will still converge, right? If you think about it, if that infinite sum approaches some finite number, you could multiply by any number, even a million, it will still converge. It's still going to approach some finite number. And same thing works for a divergent series. You can multiply by any non-zero constant, it will still diverge, all right? So you can use a multiple of a p series in certain cases, or a multiple of a geometric series if you need to wiggle around, with those inequalities for comparison purposes. Okay, so I think we showed what we need to do with just direct comparison. I didn't even need to do limit comparison. This means the sum, n equals 1 to infinity of 5 plus 6 cosine n over n squared. What does it do? It converges by the comparison test. Okay. All right. Let's look at some more scenarios. I've got a good one for you. It might be in some of your homework assignments. So we have the sum, n equals 1 to infinity, n squared plus n plus 1 over n to the 4th plus n squared. All right, so this is an. Let's see what we think it's growing like and try to determine what an appropriate choice for Bn should be. And then from there, we'll decide if we just want to do direct comparison or limit comparison. Sound good? So when picking Bn, students a lot of times have, a difficult time. How do I know what Bn is? Typically, if you have like a little rational expression like this, just look at the highest degree term in the numerator and the highest degree term in the denominator. Those are the ones that are running the show. If you think back to pre-calc days too, when you're trying to figure out end behavior and asymptotes, that's what they told you to do. Just look at the highest powered term because those are the ones in charge. So it looks like the numerator is growing based on n squared and the denominator based on n to the 4th. If I simplify that, that's 1 over n squared. So let's let that be Bn. And what do we know about the sum, n equals 1 to infinity of 1 over n squared? What do we know? It's a p series, yes. P equals 2, which is greater than 1. So this series converges. All right, if I want to use direct comparison, the original comparison test, I want to show that my terms an are less than or equal to Bn. Can I do it? Can I show that n squared plus n plus 1 over n to the 4th plus n squared is less than or equal to 1 over n squared? I don't know, because yeah, I have this extra term in the denominator, so I could say this denominator is bigger than this one, which would make the expression smaller. But then we have more stuff in the numerator, which makes it bigger than this numerator. So it's not really clear. It's not a simple inequality to show. In fact, I don't even think we can do it. So when you run into this case, you go, well, it's probably not a good idea then to go for direct comparison test. Let's use limit comparison test instead. All right, if you can't show the inequality that you need, then try limit comparison test. So we're going to look at the limit as n approaches infinity of n squared plus n plus 1 over n to the 4th plus n squared over 1 over n squared. All right, so I'm going to multiply by n squared in the numerator now. So I have the limit n approaches infinity. This guy's just going to come up here, right? N squared times n squared plus n plus 1 over n to the fourth plus n squared. Okay, I can cancel out this n squared and then make this n squared plus 1. So now I have the limit as n approaches infinity, n squared plus n plus 1 over n squared plus 1. And then next, let's divide by the highest power of n in the denominator, which is n squared. So now I have the limit as n approaches infinity, 1 plus 1 over n plus 1 over n squared. And then what's going to be in the denominator, you guys? Yes, 1 plus 1 over n squared. Okay, can we take this limit? Oh yeah, easy peasy. 1 over n, that goes to 0. 1 over n squared, you go to 0 too. So all I'm left with is 1 over 1, which is 1. Do I care what number this is? Just that it's finite and not equal to 0. So what does this tell me? That both series behave the same. Okay, the terms grow at a constant multiple of one another. So this tells me that the sum, n equals 1 to infinity, n squared plus n plus 1 over n to the fourth plus n squared, converges also by the limit comparison test. All right. Now, I do want to have a discussion about why the limit cannot be infinity or 0. Are you ready? It all comes down to your choice of Bn, what to compare it to. If you pick Bn too aggressively and it's growing faster than your terms, An, then that limit's going to be 0. Or if these terms grow a lot faster than Bn, then that's when you'll get infinity. And so it doesn't tell you anything about what both series do. That's why you have to choose Bn so carefully. That way this limit comes out to be a finite non-zero number. So when you get infinity, it'll happen sometimes when you're first starting out, or if you get 0, usually what that means is you didn't pick the right Bn, usually, okay? So if you end up with 0 or infinity, then either Bn, like if I had picked 1 over n cubed, then I would have had n cubed up here, and then my limit would have come out to be infinity. All right, you could play it out through and see. And 1 over n cubed is a convergent piece series, but it's just the wrong choice to compare it to because that limit ends up going to infinity. So just be careful, all right? And you'll see, it might take some trial and error for you to understand what I'm talking about. Okay, let's look at another one. Oh, I hope you like this one. This one was cute. I thought, let's take a break from the piece series, right? There's other stuff to compare things to. Let's spice it up. So sum, n equals 1 to infinity, 4 to the n plus 1 over 3 to the n minus 2. Ooh, okay. So what's an? An is 4 to the n plus 1 over 3 to the n minus 2. Let's see what's running the show so we could come up with a good choice for Bn. So look at the numerator. Who's in charge? 4 to the n. Like 4 to the n plus 1, that's the same as 4 to the n times 4 to the first, right? Who cares about 4 to the first? That has no power. Okay, you multiply by 4. 4 to the n. Now we're talking. That's running the show. So we've got 4 to the n. What about in the denominator? You think that minus 2 is doing much? No way. 3 to the n. So this is 4/3 to the n. I'll call this Bn. Guys, this is familiar. It's not p series though. Look at us getting wild. Sum n equals 1 to infinity, 4/3 to the n. This is geometric. Yes, yes, yes. So when we're deciding whether or not a geometric series converges or diverges, we look at absolute value of r. Whatever's being raised to the n is r, okay? So absolute value of r, absolute value of 4/3, that's greater than 1. So that tells me the series diverges. Ooh, okay. If I'm going to use direct comparison, I need to show that the terms of our series are greater than or equal to the terms of this divergent geometric series. Can we do it? So 4 to the n plus 1 over 3 to the n minus 2. We already said that's the same as 4 times 4 to the n over 3 to the n minus 2. Well, that's for sure greater than or equal to just plain old 4 to the n over 3 to the n minus 2. Don't you agree? Okay. And this is for sure greater than or equal to 4 to the n over 3 to the n, which is our Bn. Yay! Okay, so what does that tell us? That tells us that the sum, n equals 1 to infinity, 4 to the n plus 1 over 3 to the n minus 2 also diverges by comparison test. Okay, fabulous. So if I wasn't able to show this inequality, then I probably would have tried limit comparison test instead. But whoever, wrote this problem sat there so nicely, made sure the numerator was bigger, denominator was smaller, so that I could show just the perfect inequality to do direct comparison. All right, last example. Here we go. Example 5, we have the sum n equals 1 to infinity, 4 rad n over 10n to the 3 halves minus 7n plus 2. Okay, so again, let's try to figure out what a good choice for Bn would be. What's running the show in the numerator? That rad n, yeah? And what about in the denominator? The n to the 3 halves. Now, you could put the 4 and the 10 in there or not. It really won't make a huge difference, okay? I usually like to not put the constants in there, but it's up to you. So rad n over n to the 3 halves, that's n to the 1 half over n to the 3 halves. If I simplify that, that's just 1 over n, right? So let's let that be Bn. Remember, that's an. And what do I know about the sum, n equals 1 to infinity of 1 over n? That's the harmonic series, a special p series. It gets its own name. I bet all the other p series are so jealous. And what do we know about the harmonic series? It diverges. You guys, you have to write the sum, n equals 1 to infinity of 1 over n diverges. This sequence, Bn, that's a convergent sequence. The limit exists as a finite number. The terms go to 0. It's the series that diverges. So make sure you always write out that sigma, okay, when you're doing comparison or limit comparison test. All right, so harmonic series diverges. Most likely our series will diverge as well. Do I want to show that an is greater than or equal to Bn? Can we show this? Well, we're subtracting stuff in the denominator, adding stuff, messing with the numerator. It's just too much madness, So let's just do the limit comparison test. Who cares if we can show this? Abandon ship, let's just use LCT. Okay, so we're going to look at the limit as n approaches infinity, ratio of an, so 4 rad n over 10n to the 3 halves minus 7n plus 2 over bn, which is 1 over n. Okay, I'm going to multiply by n, right? So that's going to flip up there. So rad n times n, that's n to the first power, right? It's going to be 4n to the 3 halves now in the numerator over 10n to the 3 halves minus 7n plus 2. Okay, how to take this limit? No, don't even think about L'Hopital's rule. I mean, you guys, first of all, you can't apply L'Hopital's rule when you got n's in here, right? You can only use it for differentiable functions. Sequences are not differentiable, so like why bother when you can just divide by the highest power of n in the denominator? Yes? So dividing by n to the 3 halves is the same as multiplying by 1 over n to the 3 halves. And then let's see what we got now. So we've got the limit, n approaches infinity, 4 over 10 minus 7n over n to the 3 halves is going to give me 7 over n to the 1 half, right? Good. Plus 2 over n to the 3 halves. Okay, we're in good shape now. So as n approaches infinity, 7 over n to the 1 half goes to 0. So does 2 over n to the 3 halves. And then I'm just left with 4 over 10, which reduces to 2/5. I don't care what number I get. All I care is that it's finite and it's not 0. Woohoo! So what does that tell me? It tells me both series behave the same. Okay, and what series did I use for this limit comparison test? Why, the divergent harmonic series. So that means my series diverges also. And I will nicely summarize right now. So we've got the sum, n equals 1 to infinity, 4 rad n over 10n to the 3 halves minus 7n plus 2 also diverges by the limit comparison test. Lovely. You know, don't be lazy. Take the time to write your conclusion nicely. And always think about it this way. With these ones, when you're proving, you know, or determining if a series converges or diverges, imagine you're on trial, like trying to make a case, and you want to provide all the evidence clearly, thoroughly. Don't leave anything for them, for the judge or the jury to figure out on their own. You know, spell it out nice and clear so that you can be vindicated. All right, that's it. If you found the video helpful, please give it a thumbs up, subscribe, share, help this channel grow so more students around the world can find the videos and get helped. And I'm here to make math fun, tolerable, enjoyable, I dare say. So stay tuned. I'll do more sequences and series shortly. Bye, guys.